So thank you. This was some brief information on offshore platforms, how they are used, and what is the status of wind in these years. So we can now go on to the other paper presentations. Are you ready?
Hi, yes, I'm ready.
Okay. So Diane is going to present us a review of floating offshore wind turbine technologies. She completed her bachelor's degree in mechanical engineering in 2020 and then started her master's degree at the University of Malta. She now focuses on renewable wind energy and particularly on floating wind energy to apply it to Maltese archipelago and the Mediterranean Sea. So Diane, thank you for being here, for presenting this paper. Please go ahead. It's all yours.
Thank you for that kind introduction. As you mentioned, I am Diane, and today I'm going to be presenting a review of floating offshore wind turbine technologies. Can you just confirm that you can see my screen?
Yes, it works for me.
Okay, thank you. So this is a brief overview of what I will be going through today. I will give a short introduction, and I'm going to present the knowledge transfer and substructure technology, as well as introduce the mooring systems. I will present some research on fault structures using single point mooring technology. I will also present the emerging fault structures in industry, and then I will present my conclusions. So, as seen from also your presentation, there has been an increased interest in renewable energy sources. This stems from the increased energy demands, the decreased amount of fossil fuels present, as well as climate change. Therefore, we need to look for new opportunities to produce green energy. One such way is through wind energy. As can be seen in figure 1, over a period of 10 years, there has been a significant increase in installed wind capacity, most of it onshore structures. The number was expected to increase over the years. However, due to COVID, there were some setbacks. Hopefully, after all this, it will start again. It will increase again. There are two ways to generate wind energy, either by using onshore structures or offshore structures. Onshore structures have the benefits of being cheaper and easier to install, and they require less maintenance, which reduces the overall costs. However, they require a large amount of terrain to install. They also generate a fair amount of visual and noise pollution, and they also have some negative environmental impacts that affect the birds and the surrounding environment. They also encounter inconsistent wind speeds. On the other hand, offshore structures are not limited in terms of like onshore structures in terms of special limitations. They encounter stronger and more consistent wind speeds. They generate significantly less visual and noise pollution. They are much easier to upscale and have low environmental impact. Unfortunately, they are increasingly expensive to install. They require a significant amount of maintenance, and the structures are more complex than onshore structures. So in order to cope with the increasing energy demand, wind turbines have grown steadily in size. And to 2030, they are expected to reach sizes of between 50 to 20 megawatts. Although this results in increased power generation, such structures also require bigger platforms and substructures to support the turbine, which increases the mast and the cost. And unfortunately, in terms of onshore structures, this will also require larger terrain to install, which may not be possible. So the offshore wind industry benefited greatly from the oil and gas industry. First, the bottom fixed structures were developed for the oil and gas platforms. These were connected directly to the seabed. And then through continuous development, floating offshore structures were introduced that were connected to the seabed using mooring lines. As can be seen from figure 3 and figure 4, the structures used in the offshore wind industry is very similar to those used in the offshore oil and gas industry. The structures were only modified to be able to accommodate the wind turbines. The first type of offshore structures were bottom fixed structures. The most common type today remains the monopile structure, which is basically a steel tube that is embedded into the steel bed that then transitions into a tower that can support the turbine. Then there's the gravity-based structure, which uses a large mass at the bottom of the turbine to stabilize the structure and anchor the turbine. Then there's the tripod, which makes use of 3 legs connected to a steel column that supports the turbine and the turbine tower. And finally, there is the jacket structure, which is made up of multiple legs and braces that create a wide base that can stabilize and support the structure. As can be seen in Table 1, these can only be used up to a limited depth. Therefore, given the increased demand of energy and the depletion of nearshore waters, new designs were necessary. Therefore, bottom-fixed structures moved to floating platforms. These floating platforms provided better and more stable wind resources. They overcame the issue that came with the nearshore locations being depleted. There was an easier method to install the turbine. They also provided new and improved environmental benefits, given that they were not driven into the seabed, but instead anchored. They created a new business and export potential, and they also had a positive public response, given the decreased noise and visual pollution. Unfortunately, they came with some drawbacks. As these structures are increasingly complex, some of the ports found in Europe especially are not equipped to be able to construct and maintain them. They also come with complex mooring and high costs, and they also are more expensive to install. So there are three main types of float structures that evolved from the offshore oil and gas industry. The first type is the spar buoy. This is a large cylindrical structure that has a heavy ballast at the bottom. This structure has a low water plane area and is stabilized using a ballast stabilization mechanism. In this case, the large ballast at the bottom allows the center of gravity of the structure to be below the center of buoyancy. Therefore, when the structure tilts, a stabilizing righting moment occurs that counteracts the displacement of the structure. The next type of float is semi-submersible. In this case, it is made up of a series of columns and braces that are connected together. This type of structure has a very large water plane area, which also contributes to its stability. This type of structure uses a buoyancy stabilization method. The large water plane area creates a large second moment of area that provides the necessary righting moment to stabilize the structure when it is displaced. And finally, the tension leg platform. So this type of platform makes use of a very buoyant platform that is connected to a column that supports the turbine tower. The structure is connected to the seabed using tensioned tendons. Therefore, this mooring provides the tension required in order to minimize the movement of the structure. In order to introduce floating platforms, mooring systems were also necessary. Mooring was first developed for the offshore oil and gas industry. The first type of mooring system used multiple point moorings, and the first type was spread mooring systems. This type of system makes use of mooring lines spread symmetrically around the structure. This mooring system can be used in very deep waters. The mooring system keeps the structure fixed and increases the stability. There are two types of spread mooring systems. The first is the catenary mooring. In this case, the mooring lines hang freely on the seabed and they lie horizontally. So when the structure rotates or displaces, the mooring line lifts off of the seabed, and the increased weights creates the necessary storing force to place the structure back into its original position. The second type of mooring system is the taut leg mooring system. In this case, the mooring lines are connected to the seabed at an angle, and they're kept in tension. The restoring force is generated from the elasticity of the mooring lines. Finally, the second type of man-to-port mooring system is the tension leg. In this case, tension tendons are used to connect the structure to the seabed, and the high axis stiffness of the structure minimizes the motions of the floating platform. There are a number of benefits associated with multi-point mooring systems, and in fact, a lot of the current and emerging power concepts still use this type of system to anchor them to the seabed. Multiple point mooring systems provide easier installation. There's a decreased chance of mooring line failure, and they are also cheaper to install. However, the large number of anchors increase the cost as well. This does not allow the structure to weather vane. Therefore, the turbine will require a rotor yaw mechanism to align itself to the wind. A new type of mooring system that was introduced, the single point mooring system. This was first introduced for the offshore oil and gas industry. This type of system, unlike the multiple point mooring system, is only connected, make sure that the vessel is only connected to a single point. The first type of mooring system that was introduced is the buoy mooring system. In this case, the vessel is connected to a buoy, which is a single point mooring. The vessel is then allowed to weather vane around the buoy while still remaining secure. Another type of system that emerged is the tower mooring system. This is quite similar to the buoy system. However, a tower is permanently moored onto the seabed and has a bearing system to allow the structure to weather vane. And finally, the turret mooring system. The turret can be either internal or external. This is similar to the tower structure in the sense that it has a bearing system as well to allow the vessel to rotate and weather vane around it. So from the oil and gas industry, SPM systems were then adopted into the offshore wind industry. SPM systems provide a number of benefits to the offshore oil and gas industry. The first of which is that it provides self-aligning capabilities to the FOUT structure. Therefore, the structure can position itself in an ideal position with respect to the environment and can adjust itself easily depending on any environmental changes. This therefore provides more opportunity for the turbine to generate power, given that it will align itself better with the wind. Moreover, this removes the need for a rotary yaw mechanism, thus reducing the mass and the costs of the structure. As the platform is positioned head-on to the current and wave and wind forces, the floating platform will experience less weight, less force than it would with a fixed mooring system. There's also a reduced environmental impact on the seabed, given that less anchors are required. However, it comes with some drawbacks, the first of which is yaw error. In reality, there will always be some degree of misalignment between the wind turbine and the prevailing wind conditions. This will reduce the amount of power generated. The turbine therefore will operate at a considerable period of time with misalignment of the wind, which may also increase the fatigue load on the turbine blades. The structure will also experience a higher degree of motion, which can reduce the stability of the structure. And also SPM systems are more complex than multiple point mooring systems. Although a number of current and emerging FOUTs still use multiple point mooring systems, SPM systems are becoming increasingly popular because they provide the self-aligning capabilities that I mentioned previously. A number of research projects have been carried out using SPM systems. Yes?
We are running out of time, so could you please wrap up?
Okay, so there have been a number of research projects using SPM systems. Most of them show that weather vaning was successful using SPM systems. Another project provided that using a different shape, such as a trapezoidal floater shape and a voltaic tower, could increase the self-aligning capabilities of the structure. So here it shows that although the majority still use multiple point mooring systems, SPM systems are becoming more and more popular. To conclude, there has been a number of interest in SPM systems and offshore wind energy over the past 15 years. However, there still exists some knowledge gaps, and I believe that future research should focus on wave tank testing for SPM systems in FOUT structures. I would like to acknowledge that this project is supported through the Maritime Sea Award 2020 and is also part of the Venture H2020 project. So thank you for your attention.
Thank you, Diane. It's a very interesting presentation to go over how this field of study is progressing. I have a very minor comment just to give you, so it's useful. In the field, we both use recently floating offshore wind turbines and floating wind turbines. When you look at these two terminologies, you will see that floating wind turbines are more common. It's interesting just to sum up everybody's written papers, just to sum up the terminology, keep focused on one of them. And in that, floating wind turbines is more common because if it's floating, it's offshore, it's not floating onshore. So This is it's a minor comment, but I believe you'll be continuing to study in this field, so you can join us, in using the same terminology. Okay, so